So what we're going to talk about in today's video, which closes out 5.4, is just some of the applications for the fundamental theorem of calculus and evaluating integrals. So we know that the fundamental theorem of calculus states that the integral from a to b of some function is equivalent to the difference in the antiderivatives evaluated over that interval, right? So instead of just calling it some function, we'll just call it the derivative of whatever this function is. If we know that f prime of x represents the rate of change of some function f of x, which shouldn't be new to us, right? So if we have a function f of x and I take its derivative, we would refer to that as f prime of x and say that this function represents the slope or the rate of change of this original function with respect to x. So if that's the case, and we know this to be the case, then we would say that f of b minus f of a represents the change in y, because this is the difference in the evaluated values of this function while x is changing from a to b. So what the net change theorem is saying is that the integral of the rate of change, which is what we have here, right? If we know that this is a rate of change of f of x, and we're taking the integral of that, what we're saying is that the integral of the rate of change is net change. And that's essentially putting this into words. If I have a rate of change and I take the integral of that, I end up with a net change. And that's just the difference in the function's values, or the output values of this f of x function, big F of x, from a to b. And this is what we just discussed here. So this whole thing put into words is the net change theorem. So if an object moves along a straight line with a position function s of t, remember that we usually use s to denote a position function, all right, then velocity would be v of t. And something that we've discussed in the past is that v of t could also be written as s prime of t, because velocity is the derivative of the position function. So then, since velocity is the derivative of position, then we could say that the integral from some first interval in time to another interval in time of the velocity function with respect to time is equivalent to the difference in the position function over that interval. And that's just the application of this net change theorem. Rather than having f prime of x, we're using velocity, because velocity is the derivative of the position function, and so then our big F functions here are the position functions. The net change of position is displacement. Now, what if instead of wanting displacement or net change of position, we wanted total distance traveled? That would be a different situation, and we'd have to account for that in the way that we calculate this. So if we want the total distance traveled left or right, we need intervals when the velocity function is greater than 0 and intervals when the velocity function is less than 0. So if I wanted total displacement, and let's say we just have some basic function like this, all right, and this is what it looks like. Okay, this is our velocity function. Well, we're noticing a couple of things here. This first area under the curve, I'm going to call A1, that would be positive displacement. And so would this last interval, which I guess I'll call A3. But this interval here would be negative displacement. So if I were to calculate this integral, evaluate this, it would give me the net displacement, the net change. But if I wanted total change or total displacement, and I don't want to be subtracting negative intervals, and I want to know all of this just total distance regardless of direction, then I've got to think about using absolute value instead. So if I were to do that, I would have to calculate this from t1 to t2, and in this case this would be my t2 and this would be my t1, and that would be the absolute value of my velocity function, is what I would want to use here. So that would be total distance traveled. Right, so in this case, if I were doing, and I'll just use yellow here, if I were doing net change and I used my t1 to t2 of just regular old velocity, that would be calculated by taking a1 and then subtracting a2 and then adding back a3, right? And that would give us our net change. However, if we were to do total displacement instead, and we want to include that negative area as just distance, just general distance, then we would take the absolute value of our velocity function. And so that would be like saying, let's just take this distance, and then we'll add to that the negative distance, but the absolute value of the negative distance, and then we'll add to that the final positive distance. All right, so we're going to apply that in some of the examples that we're going to see here. So we have a particle moving along a line so that its velocity at time t is given by this function. And yes, this is a parabola, but remember this is not a position function, this is a velocity function. So every point on this parabola gives the velocity of the particle at a specific time t. So first we're asked to find the displacement of the particle during the time period from 1 to 4. So t is equal to 1 or equal to 4 in between those values. And if we just want to find the displacement, then that's just our regular integral. That's net change. So what we're trying to find there is what is the difference between the position of the particle at 4 and the position of the particle at 1. And we know how to calculate that. We can take the integral of the velocity function with respect to time, and we know that that velocity function is t squared minus t minus 6. So we just have to calculate this. Luckily, it's just a power rule that we're dealing with here. So this is equivalent to, we've got a t to the third, but we've got to make sure that it's a 1/3 t to the third, minus a t squared, but that's got to be a 1/2 t squared, and minus 6t. Remember, this is a definite integral. We don't need to account for the constant values there because we're going to be subtracting these anyway from 4 to 1. And so at this point we can plug in the values. So I've just plugged in the 4, plugged in the 1. Remember, I'm subtracting here, and now I can start to evaluate these. So we're going to have 64 thirds minus 16 halves minus 24 minus 1/3 minus 1/2 minus 6. All right, and in the end, I could go through the whole process of this, but we're going to end up getting negative 9/2 meters. Because remember, we're talking displacement, this is distance. So since the question is, what is the displacement, we just need a distance measurement here. All right, now part B. Find the total distance traveled during this time period. So it's important to think about what the differences are between these two situations. If I've got, I'll just use yellow, let's say this is the origin of where the point begins, and they travel this direction really far, but then they turn around and then they travel this direction for a little bit, right? We've got a lot going on there. There's some positive velocity, there's some decelerating, some accelerating of the particle, and what we've calculated here is just the displacement of the particle from the original position. So for example, we would say that based on where the particle began, it is now at a point that is about 9/2 meters to the left of where it began. But when I want total distance traveled, I'm now talking about what is this distance that it traveled out this direction. That's a number. I'm going to keep that. And then what is this distance traveled back? That's a number. I'm going to keep that. So I'm going to have these two values, and I'm going to add them together. And this is a different situation. Now I want to know what is the total distance. So this is the situation where we've got to use our absolute value. So what we're going to do is we want to know the integral from 1 to 4 of the absolute value of our velocity function with respect to time, so the question is going to be, how are we actually going to calculate this? It's not just as simple as saying, okay, well now it's an absolute value function. we've got to figure out where the critical values are of this function so that we know exactly when the function's velocity goes from being negative to being positive. So let's find the critical points of this velocity function. I'll just do that off to the side. So we've got v of t, which is equal to t squared minus t minus 6. And in factored form, I could rewrite that as t minus 3 times t plus 2, which is giving me a clue to the critical points of this function. So if I were to say that v of t equals 0, that would be the same as saying that t minus 3 is equal to 0, or t plus 2 is equal to 0. And in either of those cases, I'm going to have these possible roots of this function. Now we know that this can't be the root of the function we're talking about because with respect to time, a value of negative 2 doesn't actually make any sense here. So in the interval that we're observing from time 1 to time 4, there is a point in here at time 3 where the function's velocity goes from being either negative to positive or from being positive to negative. And we would just calculate this by plugging in some values and find that we've got a negative and then a positive. And remember, this is something that we've done in the past. I pick a value in here, maybe say 2, plug in a 2, see what kind of number I get. 2 minus 3 would be a negative 1, and negative times a positive would be a negative. However, in this range, I would get a positive. So this is where I'm recognizing that I'm going to want to split this integral up into two different integrals that I'm going to add together. I've got my first integral from 1 to 3 of my velocity function, but I'm going to want to negate that because I know that I'm going to get a negative value from there. And I don't want negative values. I'm talking absolute value. So I'm negating that value that I'll get, and I'll add that to the value of the integral from 3 to 4 of my velocity function. All right, so this allows me to play around with the equation a little bit. And what I'm going to do next is distribute that negative in here. All right, so then I'm going to integrate these, or take the antiderivative of each of these functions. So I will have a negative t to the third, but it's a 1/3 t to the third, plus a 1/2 t squared, plus a 6t. And I've got that difference in values from 3 to 1, plus the same thing, 1/3 t to the third minus 1/2 t squared minus 6t evaluated from 4 to 3. And now I'm going to calculate those. All right, just trying to fit all that in here. And now I just have to actually calculate each of these. All right, so pretty quickly we're going to end up with a negative 9. Plus 9/2 plus 18. You know, in the interest of time, I'm going to pause and fill this in. Okay, so those are all the values that we get out of here. I dropped all the parentheses, distributed all the negatives. You could use a calculator and actually combine all these. You're going to get approximately 10.17 meters. And so that number is obviously larger than the value that we got earlier when we did net displacement right here, because this is all those distances, all that distance plus all that distance, while this is just simply the distance between where you started and where you ended.